if we depolarize enough of a neuronal cell membrane, we will get what's called an action potential. So what this is it's the movement of charge from one part of the cell to another part of the cell very quickly. Okay, and the reason that this evolved is to move information across distances rapidly. So the example I like to give here is you've got a neuron that sits in the base of your spinal cord that controls the muscles of your big toe, right? That neuron's about yay long. So that's a good long distance to move information from one side to the other, right? If we were going to move ions that whole distance, it would take like an hour, right? Far too long for us to do anything useful with our big toe. However, if we just move charge from one place to another, we can do that in milliseconds, right? Because of some tricks the nervous system uses that we'll talk about later this week. So action potential is a way to take a big change in membrane potential and conduct it over a long distance so that one end of a neuron can affect the other end of a neuron relatively quickly, right? So this plays a role in moving information not just from neuron to neuron, but also from neuron to muscle, right? So our next topic that we're going to get into tomorrow and the next day is how muscle turns membrane potential into contraction, right? So we're going to connect brain to actual movement. Okay, so action potentials are all about voltage-gated channels, okay? So let's talk about those channels a little bit. All right, so here's our sodium channel. Sodium channels have two gates. They have an activation gate and an inactivation gate, okay? They are also very selective. In other words, they don't allow potassium through, they only allow sodium through. So there's a region of selectivity in the R groups of that protein. So we have three states for our sodium channel. We have resting, where the activation gate is closed, activated, where both gates are open and sodium is flowing through. And then we have inactivated, where the inactivation gate is closed, blocking further motion. So these different states are associated with membrane potential. At minus 90, we are resting. Between minus 90 and plus 35, we're in our activated state. Between plus 35 and minus 90, so in other words, back on the repolarization side, we're on our inactivation state. Now, potassium channels just have the two states. There's a resting and a slow activation. There's no inactivation gate on the potassium channel. Also, the potassium channel is a little slower to open. It has kind of a built-in delay, and that helps to keep the action potential moving in just one direction all the time. Okay. So minus 90 resting for potassium, plus 35 to minus 90. So from high to low, that's our slow activation gate. So because of the slowness here, the potassium channel opens at about the same time that the inactivation gate of the sodium channel closes. So those two things they evolved to happen at the same time. Okay. So the activation gate opens quickly when the membrane potential becomes significantly less. All right, so remember how that happens, right? Usually it's a ligand-gated channel. Some receptor has caused a channel to open, causing depolarization. That depolarization then triggers the activation of the sodium channel that comes very quickly and an inactivation that comes quite a bit more slowly. As this is inactivating, the potassium gate is activating. So we see this sort of pattern. Okay, so let's do it in steps. So here we are at a resting membrane potential. That's what we've been talking about for the last couple of days, okay? Now we get a depolarization. Why? Probably a ligand-gated sodium channel, okay? So when the membrane potential changes from minus 70 to minus 60, that's a depolarization. That causes the sodium activation gate to open. Sodium comes rushing in. Now our membrane potential is getting quite high, right? Because sodium's nurse potential is, very high in the positives. So sodium comes rushing in. Our membrane potential goes up. At about plus 30, the inactivation gate closes and the potassium gate opens. Okay, so now sodium isn't entering anymore. So we're not getting more positive. Instead, potassium is rushing out, carrying charge with it. So we go from relatively high membrane potential to very low membrane potential, close to potassium's nurse potential, as the potassium gate closes. As the potassium gate opens, the potassium rushes out. We get significant depolarization, hyperpolarization really, right? Because we were at minus 70. So we went past that. Okay, now, once this gate closes, then the sodium-potassium pump is going to pump the potassium back in, the sodium back out, and we're going to get back to our resting membrane potential. Okay? So this pattern of depolarization followed by, so we get a small depolarization at the beginning. That makes a large depolarization in the middle, which then results in a hyperpolarization at the end before we go back to normal, right? So we get this pattern that looks like this, right? So if this is our membrane potential and this is time, this is showing you the changes in conductance or permeability across the membrane. So the sodium channel opens very quickly and closes quite slowly. The potassium channel is slow to open, but closes quite quickly after we get quite a bit low in our membrane potential, right? So essentially, this is a positive feedback system. You hear a lot about negative feedback systems in physiology. That's like the thermostat where, it gets hot, so the furnace turns off and then it cools down and gets hot again, right? Well, a positive feedback system is where a small change makes a big change happen. So here, a little receptor-gated channel causes all this change in conductance to occur because of the change in membrane potential. So we get a small change in membrane potential that makes a large change in charge moving around. Okay? So if we put all those things together and we stick our voltmeter in the axon of a neuron, when an action potential goes rushing by, this is the pattern that we see. All right? So here we are at rest. At number 1, we get our graded or local depolarization. Okay? So we go from minus 70 to minus 60. Small change. But that small change is exaggerated or amplified because of the sensitivity of the sodium channels, right? When this small membrane potential change happens, the sodium gates are activated. So we get a big depolarization as sodium goes rushing in, okay? Now, once we get up here to the top, the potassium gates are starting to open. So when that occurs, potassium is going to rush into the cell and drive the membrane potential back down, right? And then as the cell recovers, it's going to go up just a little bit and back to its resting potential. All right, so this is essentially an action potential as viewed in one location at a time. A depolarization, a repolarization, a hyperpolarization, and then a